Great program? Why is that a great program? All right. So what's another way to get the same problem? Well, if I were to take the same problem we just did, sine of 30 degrees equals velocity in the equals y over, what do we call the hypotenuse? Length of the string? String. We'll call it length, L. With me so far? All right, do that. This is something brand new. Make sure you got it. Sine of 30 degrees is 0.5, right? So therefore, 0.5 L equals my y. Agreed? Now I'm going to do something completely rude. Mr. Redford, I'm going to take the derivative of both sides with respect to time. Why am I choosing with respect to time? Because that's x and y, that's y and L, right? That's the length of the string and how high it's going up. I wonder how fast they're doing these things, right? I wonder how fast I'm going to take the derivative with respect to time. Now, is this a t? Is this time? No. Is that a time? So therefore, I'm doing both of them incorrectly. So therefore, I've got 0.5. What's the derivative of L normally?
It would be just 1.
Just 1. Yeah. Okay. And then, but I have to tack on a dl dt, right? And then over here, what would happen to my y? It would be 1 times dy dt, right? We're not going to use y prime anymore because I've got weird things going on here. I'd be careful. Okay? Now, what does dl dt literally mean? Okay, what does it mean in words that other people in the hallway might recognize?
I don't know.
L was the length of the string, right?
Yes.
dl dt means the rate at which what?
The rate at which the length is changing.
It changed. And what is the rate at which the length is changing?
2 feet per second.
2 feet per second. And over here I've got y. dy dt. What's the dy dt mean?
It's how fast the y.
How fast the y is changing with respect to time. That makes sense?
Yeah.
And that would be what?
That's what we're trying to find.
That's what we're trying to find. And so if I do a little work here, I get 1 equals 1 dy dt. So dy dt is equal to 1. Units, I'm using feet and seconds, so it would be feet per second. That's the calculus way to do the same problem. I took the derivative. With respect to whatever I want to.
Yeah, man.
I find an equation, I just take the derivative with respect to whatever I want to. Anybody be thinking, well, this derivative I could do with trig, so I don't want to do it this way. Ah, that's nice. Let's talk about the next problem. I want you to read The Boy and His Kite with his new problem. And then we'll talk about why you could not use trig anymore, because trig is going to fail. Kite before, right?
Yeah.
Got it out there. The boy starts running. What happens to the kite?
I don't know.
You don't know?
Starts moving.
You want to phone a friend? Look behind you. See if you got a friend you want to call on.
George.
Trevor.
Down.
It goes down, doesn't it? If you have a kite spooled out and you start running backwards, the kite will go down. The kite dips. Okay? It falls. And the reason why it falls is because this is not changing. And because a kite can't go through the wind, it's only got one option to reduce that length, and that's to fall. Right? If you're going to increase this distance, you're going to have to decrease this distance. Now, why would trig fail us? Why can't we use the same thing? We have sine, we have height. Why won't it work for us anymore?
It's changing.
Because the angle is changing. What angle are you going to use? Oh, it depends.
No, yeah.
What do you mean? We could have called this related rates.
The angle's not changing.
If this kite starts to fall, that angle's not changing? I guarantee the angle is changing.
When at 1,000 feet?
What?
When at 1,000 feet change?
1,000 feet? That's the length of the string. Is that going to change?
Well, yeah, it's going to be straight the whole time.
Yeah.
Well, maybe we should go play with kites.
Okay, yeah, you have an additional weekend assignment for your 3-day weekend. Get a kite out and play with it. So around here playing with a kite's dangerous. Okay, but anyway, you got it so far? So if that's the case, what are we going to do? Here's what we're going to do. We're going to find a formula that would allow us to do what Redford did the last one, which is take the derivative with respect to time. To do that, we have to figure out what do we know and what do we want to know. Ms. Cohn, What do I know?
That is moving to the right at 3 feet per second.
Now, you just said that. He's moving the right 3 feet per second, but I'm not sure I like that. What's on the other side of that? We'll come back to that in a moment, because that's kind of a bad jump to jump with.
Okay.
I'm with you so far. What else do we know?
The initial
Initial, yes.
velocity? No, the
Velocity?
initial. I don't know. The initial length?
Initial length.
Yeah,
So the length of the rope is what?
1,000 feet.
1,000. That doesn't change, right?
Yeah, we know the initial height. Yeah,
What's the initial height?
5.
Can I call that y?
Yeah.
So y is 500.
Mm-hmm.
And by the way, if I know that, I also know what this is down here, right? I can calculate that. If I do some calculations, you'll just trust me on this or do it yourself. 500 root 3. For seniors, that means you won't do it. You just trust me. Okay, 500 root 3, because root 3 over 2 is the 30 degrees. Goes that. Never mind. You should have that memorized by now. All right, good so far?
Yep.
All right. If this is 500 root 3, now that's good. So that's L, Y, and X. What else do I know? I could probably figure out my angle if I wanted to. But let's not do that just yet. I'm going to go back to this little thing, 3 feet per second. Now, using these letters, what is 3 feet per second?
It's X over Y? No.
It's X over,
Or Y over X?
it's feet per second.
Yeah.
What's on the bottom?
Time.
Time. So it's, and we're running this way, right? So it's what?
X over time?
It's X over time. We don't just write X over time. We write
So,
the derivative, right?
Yeah.
The change in X with respect to time is equal to 3 feet per second. You with me so far?
yeah.
Pausing. Polito?
Change the X over, where's time?
It says 3 feet per second. Clearly that's change in time, isn't it?
Oh,
Is it not?
okay.
Now, cone. What am I trying to solve for?
The angle?
Does it say angle?
No.
What does it say?
Is it still the same question up here?
No, we're on the bottom question.
Okay.
You didn't even read it. Read the question.
Oh!
What
happens What happens to the height of the kite?
Okay, so what am I looking for?
Change in height.
With respect to
Time.
time. How do we write that?
Y over T.
But we don't write that.
The derivative of Y.
dy dt.
Yeah. How did you know the time though?
Because it asks what does it say in the question?
What's happening to it? What happens to the height of the kite?
Okay. She assumed that we're talking about speed, right? How fast is it coming down?
Oh,
That makes sense?
I guess, yeah.
Okay. Probably better if I asked the question better.
Yeah.
Okay, so now here's where things get interesting. Because the next step is going to be totally free form art mixed with your mathematical knowledge. Your extreme mathematical knowledge. And that is, I need an equation so I can Redfern it. I need an equation that has X and Y and perhaps even L in it that you know. Now, won't you talk to anybody right now? Don't you come with an equation that has X, Y, and L in it right by yourself? Write it down on your piece of paper. If you can find an equation that relates X, Y, and L. I want you to write down any equation you know from your dividend history that relate X, Y, and L in this problem. Last time you came with a sign without even asking. I need another intuitive leap. Find me an equation that involves X, Y, and L. Then Colin's going to give us her answer, and we'll see if she's got it. Resendez isn't written anything down. Miss Resendez, I expect you to be the first one done with this.
That relates X, Y, and L.
X, Y, and L. Any equation. I'm desperate, man. I need an equation so I can Redfern it. All right, Cone, you're looking over your shoulder. What are you doing that for? We're down at the bottom, by the way. We're doing the props on the bottom.
Yeah.
All right, fair enough. All right, what do you got?
Nothing.
You got nothing. You have no equation. In your vast knowledge, you've never seen an equation that would relate x, y, and L. Never once. You've never seen an equation. What? Pythagoras. That's the one.
Same.
This is a weird step. But keep in mind, we're not testing whether or not you remember some obscure formula that you learned last year in trig. We're asking, do you know some formulas? So it's always going to be a fairly obvious one.
It's not always this.
No.
Resny.
X squared plus y squared equals L squared. With me so far? Now I'm going to redfern it, which is called turning it into related rates. What did you do last time? No, we didn't. There.
Wait.
What did I do? I know I want time on the bottom. I don't have it. So now I'm going to turn it into a time equation by taking the respect to time, which I'm allowed to do. They do it to both sides, right? So with respect to time, this becomes 2x dx dt plus 2y dy dt equals 2L
L.
dl dt.
How do you have to do the derivative for all of them?
Yeah,
I don't have a choice. Do
We
ya?
always do y. Or we only do y.
We're doing whatever we have in the problem. Whatever's there, we're taking the derivative of. We don't have a choice. I take the derivative on one side, I take the derivative on the other side. Every variable is going to get hit.
So
Every variable.
we know dx dt, so we can just plug that in.
Now we start plugging things in. 2, what was x?
500 root 3.
500 root 3. What's dx dt?
3.
3, love it. Plus 2, what's y?
500.
500. What's dy dt?
We don't know.
That's what we're looking for, though, so it's okay I don't know that. 2. What's the length?
1,000.
1,000. What's dl dt?
We don't know that.
Yeah, you do.
1,000. 1.
dl dt. What does it mean? This is a
The
class we have
length.
to figure out what it means. It's not the length. dl dt is not the length. What is dl dt? What does it literally mean? The change in length
With
divided by the change in
time.
how fast is the length changing?
Not changing.
Not changing, so it's 0.
Or the length of the 1,000.
The length of the rope, the string is not changing, right? Part of the stipulation of the problem. So this becomes 3,000 root 3 plus 1,000 dy dt equals 0. I get 1,000 dy dt equals negative 3,000 root 3. Divide by 1,000, I get dy dt equals negative 3 root 3. What's my units?
Feet per second.
Feet per second. So the kite at that moment would start falling at negative 3 root 3 feet per second. The moment later would start changing, wouldn't it? Because these other things are going to start changing.
At what moment?
Ew. It's called related rates. Couldn't do that last year. This is cool.
What? We still can't do